All right. Yeah, I guess it's hard to get up this morning. It is hard for me, so I'm pretty sure that it's hard for you guys as well. Yeah. All right, so hey, just like the usual Thursdays, we'll go ahead and start the lecture quickly. And by the way, good morning to Qiandi and Yuqi. Okay, so we do have a few topics we still want to talk about because although we are in chapter 5, we will be talking about the routing functionality in network layer in general. And we already talked about two routing algorithms generally to support finding a path from a source to a destination. But how exactly these algorithms are being used by the internet's routing protocol, it's still not yet known. So today, much of the first hour is going to be about introducing how routing is done on the internet. Okay. Unlike when you see in link state routing, you know the global information and you compute based on Dijkstra shortest routing path algorithm. Or like distance vector, every node is equal and you simply pass these distance vectors that you compute based on the best information you have. Internet routing actually runs in two levels of hierarchy. Because I don't think that it's possible to treat every router equally and run link state routing or distance vector routing one way or another. In link state routing, you need to store the global graph in each and every node. Okay, that's not gonna scale very well when the internet grow, right? And distance vector, you know that it is hard to debug in case there's a problem somewhere. And so you definitely don't want the network that you run distance vector on being too big, too complex. And you don't want that network, there's a certain part that you don't know well. So for the internet, we actually run it in two levels. At the lower level, many of the routers will work together as a family, as a autonomous system, as you see in the topic here. So there's a domain or an AS of routers working together, and there's a network admin that decides what kind of intra AS routing it runs. And then many of these domains at the higher layer will work together. So each domain, you can think of it as a one node, right? And there are many domains, therefore many nodes. And these domains will connect to each other, just like routers, right? At the lower level, interconnect with each other. So at the second level, at the higher level, you also have a graph. And so you could run another routing algorithm on it. Okay, so two levels of hierarchy. And this video here is to introduce formally what is an AS. Next, we'll be talking about two routing protocols that are actually running on the internet. First is called the OSPF, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, BGP, is then based on the other routing principle, the distance vector routing. Well, to be exact, BGP is not just distance vector routing. It's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, okay, OSPF is the routing protocol that runs predominantly within a network, a local network. While BGP, this other one, very, very critical, very, very important, is running on all these backbone routers, okay, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple, and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. Okay? So until now, the way we're introducing these routing algorithms is actually very idealized. Okay? Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. even taking a distance vector routing algorithm, which is already more scalable than link state. If we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, okay, there's going to be how many? Yeah, these many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, okay, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes, okay, for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like, close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not gonna work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch, okay, you don't wanna go there. Okay, so even if we use a more scalable routing algorithm, distance vector, okay, consider it working on the internet, not gonna scale. Okay, we cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also going to swap the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 gigabyte of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay? So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers nearby belonging to another organization, another system. Now each of these systems can work independently. The network admin hired by the organizations could decide independently, autonomously, okay, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, okay, the system admin can decide maybe distance vector routing is better, okay, more scalable, better. So all routers here, they will be running the distance vector routing. Okay. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, okay, 1 or 2 routers and make them the delegate routers. These delegate routers, okay, at the higher level, will interconnect. Okay, so this system's delegate routers and this system's delegate routers, they might interconnect. Okay? And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all these routers in the backbone is going to run one routing algorithm. Okay, so distance vector or link state. Okay. Well, to just tell you ahead of time, okay, for internet, the backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. Okay. So you see 2 levels of hierarchy. Yeah, there's backbone network, and then each delegate router there associated with it is a local area network. Okay, so internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems.
Alright, so there's a little bit of construction going on near my office. I hope it's not going to be too disturbing. We'll see. So you hear from the video, internet routing, 2 levels of hierarchy. No problem. And good morning to Belang, Wei Shan, Xiaobai, and Vincent. So there are 2 levels of hierarchy. And you probably heard already, right? The routing that runs within an AS is intra-AS. Now, the routing running, connecting The ASs, okay, is the inter-AS routing. So the next video is to explain more intra-AS routing and inter-AS routing.
Once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Now, routers belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Each AS will also pick powerful routers, usually sitting at the border of the AS. These powerful routers, I call them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. So gateway is what? The doorway. Yeah, the routers sitting at the border of these AS, connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border of its own AS, and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol running in the backbone of the internet is called the inter-AS routing. Okay, so that is the routing protocol that's running across the gateway routers. So this is the routing working among the ASs, and the gateway router there will be doing the inter-AS routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have 3 ASs, 1 here, 2 here, and 3 here. You see individual routers interconnected within one AS. Okay, so there are 3 here for AS2 and 3 more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, but you see 1B and 1C, both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So these 2 gateway routers. Just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. And inter-AS routing is running in between. 1B, 2A, 1C, 3A, and so on and so forth. The focus of this slide is to talk about how would the forwarding table look like when we have 2 levels of routing running on the internet. Now, let me show you an example here. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-AS routing algorithm. It would also be contributed from the inter-AS routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, not within the region, right? You need intra-AS routing to find the gateway router. And you also need the gateway router to find, hey, where's the destination gateway router? All right, so you do need inter-AS routing algorithm telling each node where to pass data further. Just like you need intra-AS routing there telling you how to reach another router within the AS. Forwarding table here will be configured by both intra and inter-AS routing algorithm. The intra-AS routing determines the entries for destinations within the AS, within AS. And inter-AS determines entry for the external destinations. To be precise, the inter-AS determines which gateway, which router here you should be passing the data to. But intra-AS will also be telling 1D here, to go to that particular gateway router, what is the right way? So you see here, interplay of inter-AS and intra-AS routing for packets going outside of the AS.
Yeah, so intra-AS tells you how to go to a router within an AS. Inter-AS at the higher level allows you to send messages outside of your AS. Okay, so next video is to tell with an example how the intra and inter-AS routing interplay or interact.
to make sure the interplay of the intra-AS and inter-AS routing is more clear. Okay? Let's take a step back. Okay? Look at AS1 here. 1A, 1B, 1C, and 1D. Okay, so these routers within AS would run the intra-AS routing. Therefore, they would know the shortest path going to each other. No problem. Now, at a higher level, at the inter-AS routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AS1. 3A, obviously a gateway router for AS3. But you see here, 3B having also connectivity to outside to another AS. 3B is also a gateway router for AS3. Similarly, 2A, 2B, 2C all have links to outside to other ASs. So they are also gateway routers. So these gateway routers at the higher level will be running the inter-AS routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AS1 to AS2, the shortest path is to go directly from AS1 to AS2. Now, if there is another AS here, AS4, for example, okay, then the shortest path might be to go from AS1, AS2, and then AS4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AS to the destination AS? What is the next AS to the destination network? Okay. So we might have another AS here, AS5. Then the shortest path from AS1 will be what? AS1, AS3, and then AS5. With those said, we may now walk through the scenario here. Let's suppose a router in AS1, say 1D, and it's got packets to go outside of the AS. Let's say AS5 here. Okay. Now, we see the shortest AS path will be the what? A1, AS3, and then AS5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router. So this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AS routing. They do not participate in inter-AS routing, but they need still to know the shortest AS path to these destination ASs out in the world. Okay. So 1D, 1A don't do inter-AS routing, but they still need to know the inter-AS path. Okay. So they must learn the inter-AS path, which is to know for each destination AS, is it AS2 or AS3 being the next hop AS to the destination AS? And this is essentially the inter-AS routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AS routing. So 1C and 1B thereafter, inter-AS routing will then propagate these AS path information to all routers inside AS1. And so propagation of the AS path, just like computation of the inter-AS path, would also be part of the job of the inter-AS router.
All right, so essentially, each router inside an AS, although they might not be the gateway routers, they will participate in the intra-AS routing, so they know there's a route to every routers within the AS. Now, in order to send packets outside, these routers inside an AS will also depend on the gateway routers to try to install AS paths or AS routes, to destinations outside of the AS. All right. So inter and intra-AS routing somehow collaborate in this way. Now, that's the overview of internet routing, two levels, intra-AS, inter-AS routing, and there's some sort of interaction going on. Okay, just keep this in mind. Let's go into the details of intra-AS routing first, and then later we'll talk about and a lot more about the inter-AS routing that we're using. Okay, so I think Kevin have a couple questions. So let's go to the intra-AS routing intro first. Okay, so this video introduces intra-AS routing, and there are actually several options, several protocols a network admin can choose to install for their own network.
The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within NAS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of NAS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay? And then running on these internal routers within NAS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay? But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution in the 1980s, late 80s. And it's based on this principle, distance vector routing. Okay. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. Okay. But this other one, OSPF, short for Open, Shortest Path First Routing Protocol, this one on the other hand is very popular. Okay. So open here stands for open source. Okay. RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, OSPF is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, OSPF for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the IDRIP, IGRP, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking. So if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, in SDN, pretty much are doing what? Generalized forwarding, and allowing the flow table being installed, and that's pretty much all. There's no need of running routing algorithms on individual routers. So starting from 2016, Cisco stopped maintaining IDRIP because there's really no need, very little need of doing routings inside the router.
All right, so that was the options in case you will be a network admin and you need to set up the routing inside your network. So there was a question from Kevin asking, is it a necessary evil that we have to divide these routers into several ASs so that in a way we get suboptimal routes in the end? Or can still get the best solution using AS? Or can we still get the best route using AS? Okay. That's a very good question and very thoughtful, Kevin. If you think about human organization, A lot of times, these autonomous systems, they need each other. Just like human beings, we need each other. But you see that these autonomous systems can also be competitors of each other. And they don't necessarily get along, just like humans. We don't, not all of us get along. So it's a collaboration and competition at the same time. After all, internet is used by human beings. As you see that all technologies are inspired by human needs. But you see that human beings perceive something being convenient, being more usable, which might not be the same as what the engineers think the best, right? Taking the shortest time, using the minimum amount of resources. So there are quite a bit of human factors, okay, in internet routing design. Kevin, I know you're curious, which is very good. In fact, the question you're asking is very much related to internet routing being also policy-based, which you will hear about in the third topic today. And the fourth topic is dedicated to the human factor, okay, in deciding how we do internet routing, right? And Kayan was asking, how many routers are there in an AS in practice, and how we decide the region an AS should cover? Okay, that's a very good question as well. The way we kind of define an AS is usually organization centric. I think NTU has an AS, okay, because recently, because we were talking about the IP addresses used by NTU, and I realized that NTU has now an AS number. Telnet has an AS number, but somehow I think NTU is part of Telnet. So usually an AS is more a human organization. And so if a human organization has 10 routers, then that AS has 10 routers. So we don't necessarily do it this way, like, oh, there are like a million routers on the internet. And we would group 100 of them per AS. So it's not like fixed size. And it's more like based on the organization. So you might have ASs that are really big. And you might have ASs that are kind of tiny, small, relative to the bigger ones. So AS is again human organization. So what region the AS should cover? I think by region you meant probably the geographical region. Most organizations they are kind of local, so the routers within the ASs are all nearby. But there are big ASs such as international corporations. Their AS, the machines under the same AS can actually run across continents and span across the globe. So the AS are big, small, very diverse. Where they are and how wide they span geographically, also very diverse. Well, you know what? Just like human organizations, we are very diverse. Every one of us is different. Okay. Yeah, human factor is interesting. I know it's also complicated. All right, and now we're not yet done with the intra-AS routing. Among all these options, our IP is really resting in peace now. The one that's really surviving and still being used quite a bit is OSPF.
Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the OSPF. Open here stands for, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, okay, they'll be sending these reports in OSPF message. these OSPF messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all. Okay. There's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cause of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of OSPF, designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of OSPF. First of all, okay, these OSPF messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. One can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, okay, which is nice, okay, sometimes. For each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay, for example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, OSPF allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast OSPF, MOSPF, is a very nice and easy extension of OSPF. Oh, by the way, one can also configure OSPF to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3. Okay, inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay, some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. The link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at a higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router.
Yeah, so you see that link state routing is used in intra-AES routing protocol more, particularly in OSPF. Okay, and I think Kayan was asking how big they are. You see that for larger AS, you can use a hierarchical OSPF as well. That might not make it scale all that well, but at least it's easier to manage. Okay, and Claudia was asking. Okay, yeah, Vincent was saying Polly has a cat. Polly has 2 cats. Okay, for your information. So back to Claudia's question. If a router in the inter-AS level, the higher level, right? The one in charge of passing messages or passing routing information from AS to AS, then are very critical. If they fail, does that mean many of the data packets might not find a way to go to their destinations? You know what, Claudia? You are right. Okay, you are right. Therefore, in inter-AS routing, we will also want to make sure that from one AS, we have multiple gateway routers to go outside of the AS. Otherwise, if one fails, then we're screwed. All right? So, very good question, and set the stage for the next videos. We just finished talking about intra-AS, which is more or less straightforward. But inter-AS, you will see that it's quite complicated. Okay, complicated in a way that it's just quite messy. It's quite messy. As I mentioned, as Kevin was asking, okay, because internet, after all, used by people, managed by people, and people have different ideas of how they will run their network. Okay, so let's get an overview. Okay, introduction of the inter-AS routing.
Now the second big category, the inter-AS routing. There's in fact just one protocol defining the category, the BGP. Now this is also the routing protocol that runs on all these gateway routers, okay, that are higher in the internet routing hierarchy. OSPF, RIP, EDRIP, those are the intra-AS routing. So those runs on the regular routers, okay, within an AS. Now, network admin gets to choose one intra-AS routing protocol versus another, okay, as long as all the routers within the AS runs the same routing protocol. Similarly, at the higher level, these gateway routers, okay, in order to find a way to reach each other, they need to run the same routing protocol as well. You see, there's no need of having an alternative, okay, inter-AS routing protocol. Therefore, BGP here is the only inter-AS routing. Very critical. It plays the role of enabling all these packets being exchanged, okay, in the core of the internet. We'll talk more about BGP, but let me share just a little bit ahead of time. BGP here is based on the distance vector routing. To be exact, okay, it's based on the path vector routing. So in distance vector routing, the router tracks for each destination what is the shortest distance and what is the next hop, okay, along the shortest path to the destination. In path vector, okay, so this one running at the inter-AS level, the source AS will track for each destination AS what is the entire AS level path, inter-AS level path. So that inter-AS level path will contain all the intermediate ASs, okay, along the way from the source AS to the destination AS. So what's nice about keeping track of the entire AS path is this. The source AS knows by default what is the next hop AS. And by counting the number of ASs along the way, you get a rough sense of the pass cost as well. But the downside of tracking the entire pass is that the memory requirement is higher. But this is okay, right, at the inter-AS level, because we try to aggregate destination IP addresses, right, into prefixes. Okay? And if we do that as much as we can, we are not actually storing a big vector containing one entry per IP addresses. Okay? Potentially, we just have a low number of these prefixes, okay, to span the entire IP address space. So pass vector is exactly what BGP, this one and only inter-AS routing, is based on. First line, BGP stands for Border Gateway Protocol. And once again, it is the one and only inter-AS routing protocol that's holding the internet backbone together. To be more precise, it allows each AS the following. First, it allows the gateway router there for the AS to receive subnet reachability information from the neighboring ASs. This is very similar to distance vector. A router receives distance vector, okay, from the neighboring routers. So the gateway routers in the AS receive pass vector from the neighboring AS's gateway routers. So by subnet reachability information, we meant the path for each destination subnet for each destination AS. Okay? And there are many of these destination ASs, therefore, we receive the path vector, okay, from the gateway routers of the neighboring ASs. Second step, the gateway router receiving such a path vector will then propagate it to all the internal routers, okay, including those routers are gateway routers to other neighboring ASs. As a result, okay, each of these routers within the AS can calculate what is the best path for a particular destination AS. The calculation can be based on what's provided in the path vector. For example, the path length, right? Or based on the policy of the organization owning the AS. Now, this is more and more likely the case how a router determines what is the best route. Okay? The policy can well be profit-driven, business-driven, security-driven, and things like that. And in the end, when a good AS path is selected for a destination AS, the border router there, okay, then can append, okay, the AS's AS number to the AS path derived, and then further propagate this to the neighboring ASs. Okay, so that completes the cycle of receiving path vector, doing the calculation, and then pass the path vector on to the rest of the internet. And of course, okay, at the beginning, the AS gateway router will announce itself, right? So each AS is potentially a destination. It will announce itself's existence to the rest of the internet.
All right, so a few keywords here. The inter-AS routing on the internet is more like distance vector routing because it's more scalable. But it's not exactly distance vector routing. It's a path vector routing. Okay? And so you can imagine that path vector is telling, if you go this way, it will eventually reach all these ASs along the path. So that is also called the reachability information. Okay? You can also think of the distance vector as a reachability information. Second keyword, the eBGP. So those are the connections, these gateway routers that will establish. Okay, there will be quite a few of these eBGP sessions. They're TCP and connected most of the time so that the gateway routers can exchange these path vectors or reachability informations. And if you recall, right, there's some interaction between the inter-AS routing and the intra-AS routing. That interaction is supported by the iBGP connections from the gateway routers to all these internal routers, okay, routers at the lower level within an AS. And that is how how a router inside can reach destinations outside of ASs, okay, is propagated, how that information is propagated. And then from the video, okay, for the first time you see, now these gateway routers, okay, they would receive these reachability information or AS pass. They could receive multiple of these for the same particular AS destination. So they a lot of times also need to select which AS pass they will establish and ignore the others. And that selection in BGP or in inter-AS routing is very policy-based. Let me try to use an analogy. Think United Nations. Okay, there are lots of autonomous systems in the United Nations, isn't it? These autonomous systems in the United Nations, they can be connected, right? So I think quite a few countries in Europe and America, they are connected, forming an organization such as NATO. And for example, EU is also a connected cluster of autonomous systems. So you see, internet routing at the higher level, inter-AS routing, you can think of it this way. All right, now let's talk a little bit more about this reachability information. Essentially, this pass vector is the most important information the gateway routers are passing, so that they have some data to base their routing decision on.
One last point to make is just this: the reachability information, aka the pass vector. When they travel across the border, go from one AS to another AS, this is actually part of the exterior BGP protocol. So in exterior BGP protocol, we establish the exterior BGP connections to allow pass vectors travel across borders from one AS to another. Now for pass vector, that is supposed to be sent internally to all the internal routers, then belongs to the IBGP protocol, and they are sent through the interior BGP connections. And these are actually illustrated using this picture here. Okay, so if we focus on AS2, we do have two gateway routers, 2A and 2C. So you see these gateway routers connecting to other ASs. There are exterior BGP connections to outside, exterior BGP connections to outside. So eBGP, in red color. But in addition to that, 2N and 2C both need to send pass vectors internally. Okay, so you see they went through the IBGP connections. All right, so IBGP connections in blue. So once again, these are gateway routers, and the gateway routers you see having both the red connections and the blue connections. They run both the eBGP part of the protocol as well as the IBGP part of the big BGP protocol. Those BGP connections are often referred to as the BGP sessions. So these routers will exchange messages over semi-permanent connections. The reason that they're called session is probably because it's semi-permanent, so it's on all the time, and occasionally you take it down and then restart it. Okay, so semi-permanent TCP connections. Now, TCP, BGP is a routing protocol, right? These messages we send should be at the layer 3, but TCP is actually a layer 4 protocol. Okay, how do you like this? On the other hand, TCP allows reliable data transfer. So would you prefer the pass vector? So these messages that we're exchanging between the BGP routers, the pass vector is being sent reliably or not? To push it a bit further, what about using TLS, the secure version of TCP? And if we use TLS, these BGP messages, these pass vectors, would look more like an application level message. You think about it, you debate within yourself. Now, the messages we're exchanging between the BGP routers over the BGP sessions are these. The pass to all sorts of destination networks, the pass to all sorts of destination ASs. In fact, altogether, we just call it the pass vector. Okay. So BGP, again, a pass vector protocol. And let me give you an example here. So let's say in AS3, there is a prefix X. and this is the destination for packets coming from maybe AS1 or AS2. So AS3 that learns about this destination will need to announce, okay, advertise it to outside of AS3. So 3A here, okay, will need to announce, okay, its existence and pending its own AS number, so AS3 here. So this will be the AS pass, okay, being advertised. This will be the AS pass being sent in the BGP message to the other end of the exterior BGP connection, to the other end of the BGP session. So 2C here, okay, will receive the AS pass, AS3, comma, X. So AS3's gateway router 3A will advertise the pass to AS2's gateway router 2C. So when AS3 does this, it's also saying that AS3 promises AS2 to relay packet, okay, on behalf of AS2 so that it can reach destination X.
All right, so that was more about reachability information and an example. So let's take a break and we'll come back to look at another example, right? And then to tell you a little bit more about these reachability informations or the messages that are being exchanged in the eBGP sessions. Before the break, let me just answer Leon's question. OSPF, when they are exchanging messages, what protocol does it use? Is it TCP, UDP, or what? You know what, Leon? It's using IP, the native IPv4 packet. So if you can Google, and you will see that these OSPF messages will be in this format. You have version number here, type here, packet length here, check some authentication type. Yeah, so this is an IP packet. So this is a native IP packet. It's not UDP, it's not TCP, none of them. All right. All right, so time to take a break. Yeah, so there were a couple questions during the break. Tindy was asking whether the BGP session advertise each router's AS pass information in individual messages. I think it depends a little bit. One can definitely, in case a BGP router contains multiple AS pass information to pass on, uh, usually what they can do is to aggregate maybe a longer message, but one message, and pass it once to the neighboring BGP routers. But in case certain paths arrive, and which is a new one, then the gateway router might want to pass it fast, okay, to the neighboring BGP routers fast as well. Okay, I think usually these routers or these computers on the internet, they do have multiple mechanisms. When it's in the steady state, it's a periodic update. But in case there's some messages triggering, okay, certain actions, then the router might decide to quickly pass on the information. Think a little bit more like when we are doing the distance vector routing. Yeah. So when there's a update of the networks, we also get triggered and recomputes the distance vector and pass it further. But otherwise, it's periodical. Wei Xiang was asking, is network prefix similar to an ID of the AS? Yes, Wei Xiang. Wei Shan. That is exactly, okay, similar to the ID of the AS. Okay. So it's just like in intra-AS routing, right? IP address is the ID of the destination router. So network prefix is like the ID of the destination network in the inter-AS routing. So Youxiang was asking, how do two BGP routers exchange BGP messages over TCP connections? Since typically routers can have at most 3 layers. Yes, according to the end-to-end argument, right? So if this is a network layer talking to network layer protocols, then you should not be using anything that's higher level. Okay, Youxiang, you're right. So this is really odd. So between BGP routers to send the BGP information, we use TCP. And this is because very, very specially, the BGP routers, these AS paths, they are very important. Remember Claudia was asking, right? What if the router failed? What if the message, okay, was lost? What if the AS pass information was lost on the way? Yeah, now you get the bigger picture, okay? And so, of course, you can implement a reliable transfer protocol at the IP layer for BGP. But that's also a lot of work. They thought that we might as well just use TCP there. So Youxiang, you're right. You're not comfortable with that. Many of us, many of the network engineers, particularly the architects of the internet protocols, are very unhappy about this. But this is a really nice hack for the problem here. All right, so you see that internet routing is quite hacky, in fact. Good. Now, to sort of impress you with how inter-AS routing is working, let's go through another example, which is a little bit more complicated, and you will see that a BGP router might receive multiple AS passes for the same destination network.
Let's go over a couple more examples so it's more clear where the import policy and the export policies are applied. So this is the same example we saw earlier. Destination network is here, X, okay? And so AS3 there is gonna send the pass advertisement. Okay, that looks like this, AS3, comma, X. Okay? And this is gonna reach 2C of AS2. So AS2's router 2C receives pass advertisements like this. And this is through the exterior BGP connection. And the advertisement came from AS3 and from router 3A. So 3A of AS3. Now, yeah, if you recall in the very early slide, right, the border router here will then propagate the AS path throughout all routers in the network. But no, there's import policy. So Yeah, the exact process is more like this. 2C there will actually check AS2's import policy. If the policy says 2C, it's okay to accept the pass, then 2C propagates the pass to all routers internal of AS2. So sending of these AS pass internally is through the interior BGP connections. Alright, so the import policy actually happens before the propagation of the pass, to all the routers internally. And then, 2A here, receiving such a pass, can then prepend itself and pass it further to the neighboring ASs. But wait, the export policy is applied here before passing on of the advertisements. Let's check. If 2A here is allowed to advertise the discovered pass to AS1 here, then we form the new advertisement AS2, AS3, and X, and then send it to 1C that belongs to AS1. So once again, before the prepended, the extended AS pass can be advertised further to the rest of the internet, we check the export policy. Second example is a bit more realistic. So 3A here, the gateway router of AS3 might have multiple eBGP connections to outside. So in that case, a gateway router might learn multiple paths to a destination in AS3. So let's see. One of the paths is this, right? AS3's 3A sends AS3X as an advertisement to 2C. 2C checks the import policy and therefore pass it on to all the routers internally. 2A picks it up, checks the export policy, and let's say that it's just allowing advertisements of the pass further. So prepend AS2 to the pass and then send it further. At this point, 1C learns the pass AS2, AS3 to destination X. And the way to go is for 1C to send to 2A. The other direction is this. 3A can be simply sending what? AS3X, this past advertisements directly to 1C, and 1C will just simply learn, right? There's another way to reach destination X, which is just simply sending it to AS3 through 3A. So these are the gateway border routers that 1C send the packets to, for the two different paths, 2A and 3A. At this point, 1C sees two advertisements coming in. Before 1C propagates any of the paths further, it needs to check the import policy. So AS1's gateway router 1C there, we need to choose. It could choose one of the two, or it could just take both of them. Let's say that 1C chooses AS3, X, sure, the shortest AS path, and advertise it to all routers internally of AS1. This is the second example.
So those are more examples. And you see this time, there's route selection on the BGP routers that have advertisements coming in, right? So that's the import policy route selection. And hey, at the exit point, there are these BGP routers that connects to other ASs. They might be sending the AS passes further. There's also a export policy. So you see that these BGP routers inside an AS, they can be configured to decide what path we take. And they can also be configured to decide what path we export. Now, there's one more message. This is talking a little bit more about the message we exchange. Essentially, inside the message, there are, of course, the AS path, right? There are actually a few more other things.
Let's say more about the messages we exchanged in these BGP sessions. So these messages are essentially pass vectors. Inside the pass vector, we have lots of these pass entries, or route entries. Each pass in the pass vector of BGP is this: the destination address. Now, because in BGP we are sending packets to a destination network, therefore, to address to a destination network, we use the prefix of the destination network. And then attributes. Now, in pass vector, the most important information there is the path. Therefore, you see, okay, in the set of attribute here, we need to definitely have the AS pass. So AS pass is the most important component in the set of attributes. There we see the list of ASs, okay, it takes from the source to reach the destination. The discovery of the list of ASs, the discovery of the AS pass, however, okay, came the other way, from the destination network. Okay, so the destination network is going to advertise its prefix, okay, and so that's going to be in a advertisement message. Okay, so the home AS of the network X, okay, let's say AS2, okay, receiving such an advertisement at the gateway router, okay, that gateway router is going to prepend itself, okay, prepend the AS number, okay, AS number 3, okay, before X, and send this out as the prefix advertisement to the neighboring AS. The neighboring AS, let's say AS2 there, receiving such, okay, an advertisement is going to prepend itself before it sends out further to AS2's neighboring AS. Okay. So now AS2's neighboring AS receiving such an advertisement will then discover, right, a path to go from AS2, AS3 to destination X. Okay, so list of ASs through, okay, these paths, the prefix advertisements as traversed. Okay. So that is the AS path. One and the most important, okay, part in the attribute set. Second important is this, the next hop. Now this is not quite, okay, the next hop AS, the next AS number, okay, in the AS path. No, it is actually the gateway router, okay, within the source AS that is directly connected to the next hop AS. So it's carrying the IP address, okay, of the gateway router, leading to the next hop AS. So the two together necessary forming the attribute set. Now, BGP routing, okay, has grown more and more being policy-based, okay, meaning the gateway router, they're receiving these prefix advertisements, okay. It's not like for every advertisement, they will actually prepend its own AS and then pass it down further to other neighboring ASs. There'll be some sort of import policy, okay. So the gateway there receiving the advertisements will have to say, okay, will have to decide. Some of the advertisements they will decline, and some others they accept. Only the ones they accept will be propagated further to all the routers within the AS. Okay. Now the gateway routers, okay, in the AS receiving these accepted, okay, advertisements will then decide whether to prepend themselves and then pass the expanded advertisements, okay, to the other neighboring ASs. Okay. But you see, there are also policy, okay, the AS might apply before these other gateway routers, okay, advertise the expanded, okay, AS path to the neighboring ASs. Okay, so some of them actually might have complex policy that is very fine-grained. For example, if one gateway router, okay, connects to two other neighboring ASs, this gateway router might say, I send this particular extended advertisements only to one of the ASs. Yeah. Policy to import and policy also to export.
Alright, so that was just the BGP's overview. We have 3 more videos that explains exactly how the forwarding table is sent. So far we just talked about the routing messages being exchanged. We have not yet talked about the forwarding table. Okay, that is actually the most important topic that's coming up in part 4. Okay, and here's the first video telling exactly how the inter-AS routing working with the intra-AS routers to set up these forwarding tables.
Let me borrow example 2 here and continue to talk about this. How a router sets up a forwarding table entry, okay, for a destination outside of the AS. Okay. Yeah, scenario the same, destination being X. 3A, the gateway router of AS3 has 2 eBGP connections, therefore 1C here potentially can receive 2 AS paths. And 1C, according to example 2, chooses the shorter AS path. So let me run the animation. So 1C discovers 2 paths and picks the shorter path. Okay. And this shorter path is further propagated internally to all routers. So 1A, 1B, and 1D will learn about the shortest path to destination X from 1C. Okay. And what 1A, 1B, and 1D will do is, well, if I receive ever any packets with destination X, then I will forward the packet towards 1C. The border router, okay, they receive, okay, the AS pass file. Okay. Now, to make it easier to explain what's coming up next, let me just label, okay, for 1A, if the packet is supposed to go out on this interface, then we call that interface 1. And yeah, for packets to go out on this other interface, let's call it 2. Okay, similarly for 1D, this is interface 1, this is interface 2. Now, 1D here, okay, has discovered there is a pass to destination X that is going through 1C. Okay, that is what 1D knows so far. To add an entry into the forwarding table for X, 1D needs to know exactly which interface, is it 1 or 2, that leads to 1C. How would 1D know that? Yeah, call the intra-AS routing there. Okay, let's say it's OSPF. Okay, so OSPF is going to tell us if the destination is 1C, what is the link, okay, along the shortest path to 1C. Okay, so that happens to be 1, so we will fill this entry here. Okay, interface column being 1. Similarly, let's try to derive again for 1A. Okay, so 1A knows, for destination X, I should be forwarding packet towards router 1C. So let's call intra-AS routing and find out from OSPF, what is the shortest path to 1C and which link, is it 1 or 2 on the shortest path? And we'll get 2 here, and 2 here would forward packets to 1D. And 1D here we see earlier will be forwarding packets over this direction and reaching 1C. Therefore, going backwards and reaching destination X.
Alright, so you get a rough idea how the forwarding table is set up. Okay, now here's more.
Route selection. Now this mechanism is necessary for slightly more complicated scenarios. Let's go back to example 2 again. Right? We have this router 1C being the gateway router of AS1. So you see towards the end of the scenario, AS1 discovers 2 AS paths, one from AS3 to go to destination X, the other from AS2, and then via AS3 to go to destination X. So in the previous slide, we say the policy of AS1 is such that we only select this to import. And so 1C propagates this AS path to all internal routers. Internal routers will then send packets, destination being X, through 1C and therefore being forwarded to AS3. Very simple. But what if we relax the import policy a little bit further so that 1C here cannot discard this other AS path? As a result, 1C will need to propagate both paths internally. So each of these routers internally will see more than one route to the destination X. Ouch. Yeah, so that's when we apply the route selection. So internal router there will need to apply route selection here to decide which of these two it will send packets to. The process is like this. Step number 1, check the local preference of these routes. So if you recall earlier, a route is what? Composed of the destination network's prefix and a set of these attributes. So we know that AS pass is one attribute. Next hop is one attribute. There's one more attribute called the local preference. So this one actually weighs the highest. So BGP actually checks the local preference first and take the path with the highest local preference. So local preference there is usually to indicate, between the two neighboring ASs, AS3 versus AS2, does AS1 prefer forwarding packets to AS3 or AS2? So if AS3 is preferred, AS3's path, so this guy here is going to carry a higher local preference. Now, if there's no local preference specified, then we go to step 2. So the internal router, let's say 1D here, will then check which of these multiple paths to destination X give us the shortest AS path. So in the scenario, 1D is going to pick this one. Now, if both AS paths have the same path length. Then we go to step 3. We pick the closest next hop router. Okay. Yeah, 1D here sees 2 paths. Okay. The next hop router for this path is going to be 1C. The next hop router for this path here is going to be 1C as well, because 1C is the border router, okay, receiving, okay, these advertisements. But if you consider, okay, a slightly different scenario, okay, so again, we have AS3, AS2, and AS1. Okay. And, okay, so the router now in the limma is now 2D. Okay. 2D here actually sees 2 AS paths. One AS path is actually coming from 2C. 2C is the gateway router connecting to AS3, okay, which it receives a path to X, AS3, X. 2A is the gateway router connecting to AS1, where AS1 is passing another AS path, okay, to AS2. That is AS1, AS3, and X. So 2A passes this path to 2D. 2C also passes on this path to 2D. Okay, so 2D in the end learns, okay, there's one AS path through next hop to A, this guy. There's another AS path through 2C, this one. 2D here, okay, assuming that abandon the shortest AS path phase, go straight to the closest next hop router phase. Then we'll do this. For this path, next hop router is 2A. For this path, next hop router is 2C. 2D here will consult, okay, the intra-AS routing again to find out, is 2A closer or 2C being closer? Okay. So if you see the scenario, 2A distance to 2D is only the link cost between 2A to D, which is 201. Distance between 2D to C, however, is 263. So 2D here is going to choose 2A to forward the packets to. So it's going to choose AS1, AS3, and X, this other AS path, which is actually longer, okay, than this other one to pass the data. This is also very well known as the hot potato routing. Allow me to explain. Yeah, so 2D is this guy holding a hot potato. So yeah, the packets are almost like these hot potatoes, and 2D can't wait to get rid of these packets. So 2D wants to be able to pass the hot potatoes, the packets, as soon as possible. Therefore, picking, okay, this poor guy here, 2A, to throw all the hot potatoes over. Okay, distance is shorter. Okay.
All right, so hot potato routing. So some of you guys might be thinking, right, in earlier part of the video, I said that, hey, there's policy deciding whether we pass or select a path. In case there's no policy, then we take the shortest, right? And then last, there's still the next hop and the hot potato routing. Okay, you see that in the example, there's one path, which is I think AS3 and X coming from one way, and then there's AS2, AS3, and X from another way to an internal router. Okay, so this internal router, by the way, does not choose the shortest AS because it's not a BGP router. But it does do this potato routing. There are 2 next hops to choose. And both of these paths go to destination X. And so what it does is simply find the shortest path in the intra-AS routing to one of these next hops. All right. So BGP, really strange. Okay, and the interplay of BGP to the lower level routing also somewhat strange. But you can probably imagine that ASs can be big and small. So that shorter AS path, for example, AS3X versus AS2, AS3X, the difference in terms of the router hops might not be all that big. Not to mention that there could be traffic ongoing. Okay, so choosing a shorter AS path or longer AS path don't necessarily give you better performance. Okay, and that is why hot potato routing is kind of a greedy, a local greedy decision, right? So that internal router, whatever, I don't care the AS pass. I'm gonna just pass my data to the next hub router that is the closest. Okay, I optimize locally. All right, so for setting up forwarding table is something addition. And the last few videos are about passing the routes, sending these reachability informations, discovering the routes. Okay. There's just one more video about the message types in BGP. It's more straightforward.
This is the last slide of the BGP protocol. Okay, so in BGP, the protocol, it actually defines 4 types of messages. Okay, so not just the message we mentioned earlier, containing the pass factor being passed in the BGP sessions. Okay. There are other types of messages that BGP sends. So some of them are actually to send the pass advertisements, to send the pass factors, but some of them are to establish the TCP connections, okay, for the session, or to tear down the TCP connection, or to keep the TCP sessions alive. Okay, let's go through these BGP messages. The first type is called the open message. Yeah, the first purpose of it is to establish the TCP connection. Okay, so the sending peer there will be sending an open message to the receiving peer. Okay. Receiving peer will be sending back an ACK for that message. As a result, the 2 peers establish a BGP session. So the ACK of the open message there is going to be in the keep alive message format. Okay, I know it's a bit tricky. Now, the open message is also used to do the authentication. Okay, so the 2 peers can authenticate each other to make sure that the pass advertisements, okay, are indeed the true pass, okay, to be discovered. Now, update message. So this is the message being used to send the past advertisements, the past factors. So this message is also allowing the routers to withdraw outdated pass factors. Keep alive message we saw earlier, it's to ACK the open message to establish a TCP connection. Keep alive message is also being sent, okay, periodically to refresh the TCP connection, just in case there's no update messages being generated. So update messages is the past advertisements. Last is the notification message. Okay, so this reports in case there's any error in the previous message. Okay, and it's also used to close the connections for peers.
All right, so yeah, Wei-san was saying that hey, after we propagate an AS pass, for example, AS3X, internally within AS2, and the link between AS2 and AS3 broken. That is super bad. You are right, Wei-san. Yeah. So just like what Claudia was having an intuition about, right? So if these BGP gateway routers somehow malfunction, or the links between the gateway routers somewhat malfunction, yes, that's going to create some sort of network outage for some time. And therefore, until today, there are actually many researchers like Polly investigating how we discovered problems in the core of the internet. And sometimes it can be just BGP router misconfiguration. All right, so we do have to pass. Definitely, you want to maintain some redundancies, and therefore you don't want to be too strict selecting the path to import and selecting the path to export. And you definitely want to keep connectivity. You see that on the internet there are many ISPs, and these provider networks, they are all businesses. And you know what, ISP to ISP, they are also competitors. But if they kind of break a connection, that's going to be bad for everyone, not just the 2 of them. You create disconnected routes, disconnected islands on the internet, right? So you kind of divide things into big camps. The ASs into big camps, like, you know, United Nations, sometimes they are big camps. Is that good? Usually not a good thing. And both sides suffer. All right. So let's talk a little bit more about these, you know, human factor complexity, the BGP routing policy. And let me introduce why Okay, there are all these policies. Okay.
One very important issue about BGP to discuss here is, BGP routing is very policy-based these days. If you recall, there's import policy, there's export policy, there's also local preference for route selection. There are lots of things the network admins can tweak, to decide where packet goes. The reason for those policy-based settings is this. Let me use an example to explain. Consider this network. We have three ISPs in the middle, ABC, they are the provider networks. W, X, Y are the customer networks. More specifically, W is the customer of ISP A. So W pays A some amount of money every month, and A will in turn help W passing packets, going out to the rest of the internet or coming in from the internet. Similarly, if the traffic is supposed to go out the other direction, right? So W pays A, and therefore A is responsible to serve W. Similarly, for this customer-provider pair, Y being a customer, C being a provider. X being a customer, B being a provider. Now, X is a little bit more complicated. It's multi-homed, customer network. So X here pays B and C. As a result, B and C should both be forwarding packets for X. In scenario 1, let's assume that there's a user in customer network Y here wanting to send something to the user in W. And so in order for W to draw in traffic from the internet, its provider A here will need to announce its existence. So AW here, an AS pass needs to be sent to the neighboring ASs, which happen to be ISP B and ISP C. So A advertises pass AW to B and to C. As a result, B is going to see this pass and prepend itself and see if this AS pass needs to be further advertised to yet another neighboring AS, such as provider C. Now, B's network admin actually knows better and choose not to do that. And the reason for that is because of this. If BAW is advertised to C, C is going to discover, this is actually one way for this user in Y to send traffic to user in W. And therefore, the traffic is going to go this way to W. And you know what? B here, B does have a customer X. X is paying B. But is W paying B? Is A paying B? Is C paying B? Well, based on the setup of the problem, WAC not paying B, and yet B is using the network resource here to transit the traffic for B and C. So B gets no revenue to do this route, BCAW, because CAW, based on the scenario setup, not paying B. So chooses not to advertise BAW to C is so that C does not discover this pass, and therefore, not using this pass to send traffic. Instead, C here receiving AW is going to prepend itself CAW, and Y is going to use CAW as a way to send traffic to the user in W. So you see, in this scenario, very obvious. For a customer network, ISP will be happy to route traffic to and from the customer. But the ISP not getting paid by others would hate to transit traffic between these other ISPs. So bottom line, not getting paid for the work. Scenario 2 is very similar to scenario 1. The network is completely the same, and we just continue scenario 1 from here. When B has discovered BAW is a pass to go from B to W. Now back in scenario 1, a min of B chooses to not forward BAW to C, so that we don't draw traffic this way. Nice. But B will actually have to send BAW to X, so X can discover XBAW is a pass. So just in case there's any user in X wanting to send data to user in W. Nice. So makes sense. But hey, X is dual home, so there's yet another connection to a neighboring ASC. So should the network admin of X here send XBAW to C? Well, let's assume that we send XBAW to C. In this case, C is going to discover CXBAW is a path to send data to W. Similarly, Y is going to discover YCXBAW is a path to send traffic. YCXBAW is a path to send traffic from a user in Y to a user in W. And that's going to travel like this. How do you like this? Well, from an X's network admin's point of view, hey, this traffic is actually not for me at all, right? It's actually between Y and W. Y pays C, W pays A, and no one is paying me, and yet I'm paying B and C. Okay, so it's a big no-no for X here to send XBAW to C. All right, so X will not want traffic coming from C and simply transiting to B. So X should not be advertising anything to C, okay, coming from B. So again, money is the issue, all right? So X is not getting any money from C or from B. Therefore, X is not happy transiting traffic for these other ISPs or even from other customer networks not paying. Okay.
All right. Yeah, money is a big issue. And that takes us to quiz 47. You see, the scenario is very similar. We have ABC being the providers, and XYZ being, XYW being the customer network. Okay. And here in this scenario, let me just add one more condition. Y here very often wants to send data to X, so traffic needs to be drawn this way. All right, so X is the customer. X is the customer of B, so X pays B. B being the provider, in exchange of that money, forward traffic for X. And so you might notice that this network is different from the examples in the video, so there's no connection between B and C. So this is a tree network. Okay, and let me ask you, Q1, should B advertise the AS path BX to A, and why? Q2, should A advertise the AS path? So if BX is advertised to A, and A here can then advertise ABX further, right? So that needs to go to W for sure. Should it be sent to C, and why? Okay, so pick your solution and justify. And you have only 2 minutes for this quiz. Okay, counting. All right, so I see you guys come up with various solutions. So for Q1, definitely yes, right? For Q2, yes and no. So if A is nice, ooh, I think there's a curse quake going on here. There's a little bit of shake. I hope it doesn't last long. Wow. Hey guys. Should we go duck? Oh, okay. So it's finally easing a little bit. It's a very interesting shake. Ow. Okay. Tension's off. I actually am not quite sure when in such a case whether the stream needs to be interrupted or not. Good that it kind of eases down gradually. Okay, yeah, let's come back to the quiz. Anna, yeah, we kind of get used to it, but this is not a good demonstration. You should try to find places that you can duck. Under the door frames or next to the bed frames. Yeah. Okay, so don't do what Polly does. I'm kind of just sitting here hoping that it goes away. Duck under the table, desk, lay down next to the bed frames. Yeah. But like, now there's a lot of butterfly in Polly's stomach, in fact. But you know, the sense of responsibility is actually keeping me here. Okay. Yeah, so hey, I'm not sure if you guys are ready for this. For Q2, answers is more or less good and yes or no. If A there is a nice guy, then definitely propagate A, B, X down to C. And if not, then of course A can be selfish because Y is not A's customer anyway. You know what? You get the reality of of the world. All right, so shall we go down to the next quiz? The complexity is a little bit higher. You see also the money flow a little bit more clear. And the main differences between quiz 48 to 47 is that now there's a connection between B and C. All right. Otherwise, Y sends very often to X. Okay. Now, Q1 asks if A and C charge B, A and C charge B. So B is actually a smaller ISP. Usually a newcomer needs to pay all the old-timers, bigger ISPs to get access, to connect to the internet. Okay, so A and C charge B for some money so that B can forward his customers' traffic to A or C. Suppose you are now hired by B. Okay, you are now joining this new and young ISP. Suppose B advertised BX to only and you are the network admin. Should you advertise BX to A, to C, to both of them, or to either one of them? Okay. Q2. That's assumed. Now, C and A, these two big ISPs, old timers, kind of charge you differently. And let's see. If C charges B more, and A charges less. So BC money flow bigger. BA money flow thinner. Again, you are working for B. Should you advertise BX to A only, to C only, to both of them, or at least one of them. Okay, so for either Q1 and Q2, justify, give your reason. All right. So for that, let's also give you guys, what time is it now? Oh, okay, so 2 minutes. Okay, and unfortunately for the policy quizzes, we actually have 4. We actually have 4, but we only have time to do it in class. Okay, for 2 of them. So for the other 2, I would advise that you guys work on them after the class. Consider it a take-home quiz. Okay, good. All right, so work on it. Yeah, so I can see that, for example, agent is saying in Q1, at least one of them. So at least there exists a path. So B announces the reachability of his customer, at least to one of these guys. Okay. For Q2, agent will then choose to send to A only because I guess it's because you're paying A less, right? So the cost is lower. Very natural. And very wise, business-wise. And team 14, I see. Oh, they think that for Q1, B should forward BX to both A and C. Because, hey, W might want to send data to X as well. Just like Y wants to send data to X. Okay, that's a good reason. Because you don't know when W wants to send data to X. For Q2, blank team 14 also chooses to forward to A. Because it's cheaper, I guess. Yeah, for the same item, for the same service, if one is cheaper versus another, which one do you choose? Okay, so team A, Naiming is saying both when they are charging you equally. Interesting. Set a reasonable upper limit and advertise to all parts within the limit. So I think it's kind of a low balance way. So you advertise both paths, but you somehow limit the rate of traffic coming in and out. That's a way to control the expense, definitely. Okay, so it's a combination of setting the routes and limiting traffic. It's a very interesting way of getting around the problem. So team 6 should advertise to both, but at least one. Okay, so better both, but at least one. Yeah, so when there's not much money issue, then you would try to do what's the best for the customer and the community. But if there's money issue, then you think more. So these 2 quizzes, in fact, the 4 quizzes, to make sure that you are aware. There's a good reason the BGP routing is policy-based, because when it comes to money, people think again and try to optimize either revenue or profit. Right? Makes a lot of sense that BGP routing is policy-based. All right, so that is all the time we have for this semester, in fact. Okay, so please do work on quiz 49 and 50. And I will see you next week for the last exam. Okay. With that said, okay, so hopefully it's not too much trauma for our international students. Yeah, but really, you want to duck just in case. And with that said, that's all for the semester. All right, and here's the music. Merry Christmas! Xiaobai, give me a second. Let me end the stream first, and then I'll come to your question.